Hello, everyone. Today, we are going to discuss explicit formulas for cyclic sequence. The first four terms of the sequence are 2, 0, 2, and 2, and repeat the pattern for the rest of the terms. We want to find an explicit formula for the sequence. That means we want to express x of n as a function of n. We also call the explicit formula as closed form formula in compare with the recursive formula like x of n plus 4 equals x of n. Here's the agenda. First, I'm going to introduce an interesting solution using remainders when integers divided by 4. Then I'm going to introduce another approach using geometry sequence that satisfies the same recursions. Using a linear combination of the 4 sequences, we will be able to replicate the target sequence, the one for 2, 0, 2, 2. I'm also going to discuss a linear recursion in general and their characteristic polynomials. And we will use Fibonacci sequence as an example to show how to derive explicit formulas for such sequences. We define another sequence, an, as n minus 4 times the integer part of n divided by 4. We use the bracket of x denotes the largest integer less than or equal to x. If you calculated a few terms of an, you would find the pattern. A1 equals 1, A2 equals 2, A3 is 3, and then back to 0. And then 1, 2, 3, 0, 1, 2, 3, 0, and so on. In other words, an is simply the remainder when n is divided by 4. Now we have another sequence with 4 numbers repeatedly. So 1, 2, 3, 0, 1, 2, 3, 0. If we can find a transform, a function that converts 1, 2, 3, 0 to 2, 0, 2, 2, then the function can convert the sequence to our target sequence. The one will be repeatedly 2, 0, 2, 2. Well, a cubic polynomial would do the work. So we have f of 1, f of 3, and f of 0, all equal to 2. Then we can assume f of x equals a constant a times x minus 1 times x minus 3 plus 2. If you plug in 1, 3, and 0, the product is 0, and you got the constant 2. We have another parameter a to be determined. Fortunately, we have one more condition, f of 2 equals 0. Plug it in, we have a equals 1. Then the function f of x is x times x minus 1 times x minus 3 plus 2. And finally, our target sequence x of n equals this stuff. We replace every x in by n minus 4 times the integer of n divided by 4. Another way to solve the problem is to use geometric sequence. Let Tn is theta to the power n that satisfies the recursive pattern Tn plus 4 equals Tn. Plug it in, we have theta to the power n plus 4 equals theta to the power n. Then theta to the power 4 equals 1, which have 4 roots, 1, -1, I, and -I. Then we have 4 sequences. The first one, an, is 1 to the power n, that's 1, 1, 1, 1, and so on. The second one, bn, is -1 to the power n, -1, 1, -1, 1, alternatively. The third sequence, cn, is I to the power n, I, -1, -I, 1, and then back to I, and so on. Repeat every 4 numbers. The last one, dn, is -I to the power n, -I, -1, positive I, positive I, positive 1, and so on. You know, this sequence, if we multiply a constant on this sequence, it will also have the same recursive pattern. Moreover, if we have a linear combination of these 4 sequences, it will also follow the same pattern. Our goal is to find 4 constants P, Q, R, and S, so that the combination with these 4 constants will replicate our target sequence, the 2022 sequence. The first sequence times P, we got the P, 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 and so on. The second sequence times Q, -Q, positive Q, and so on. And the third and the last. Sum up, and the first 4 term should be 20 and 22. This way, we establish a system of equations for P, Q, R, and S. They are easy to solve, and they are all real numbers. P is 3/2, Q is -1/2, R and S are 1/2. So we got the explicit formula for the 2022 sequence. This looks much nicer than the previous one. The cyclic sequence we just discussed is a special case of something called linear recursive sequences. A sequence is said to be a linear recursive sequence if the linear combination of some consecutive terms is 0, and with some constant coefficient ck, ck-1, and all the way to C0. In general, we assume ck is not 0. Then the largest term, a of n plus k, can be expressed as a linear combination of some of the previous terms. Looks complicated, but I can give you a couple of examples. The 2022 sequence. This is the linear combination expression. Another one, the famous Fibonacci sequence. Every term is the sum of the previous 2 terms. Here is a very important property for linear recursions. Let an equals theta to the power n, a geometry sequence where the base theta is a root of a polynomial ck(x to the power k, ck-1, x to the power k-1, and so on, plus c1x plus c0. Pay attention to the coefficients. Then this sequence will be a recursive sequence, literally linear recursive sequence, with the recursive relation like this. the coefficient is determined by the coefficient of the polynomial. It is easy to verify. We plug in the definition for the sequence on the left-hand side of the equation. That's an equals theta to the power n. We got this. And then factor out theta to the power n. Remain in the parentheses is actually the polynomial plug in theta. And we know theta is the root. And of course, we end up with 0. The polynomial is called characteristic polynomial of the linear recursion. Characteristic polynomial is an important concept in many areas of mathematics. For example, ordinary linear differential equations. So for details of linear recursion and their characteristic polynomials, if you are interested, you can Google the concept to find more materials on the web. And finally, I will derive the closed form formula for Fibonacci sequence. The linear recursion is f of n plus 2 minus f of n plus 1 minus fn equals 0. The coefficients are 1, -1, and -1. So its characteristic polynomial is x squared minus x minus 1, which has two roots, x equals 1 plus or minus square root of 2, square root of 5 divided by 2. Then we can create two geometry sequences using the root. They both satisfy Fibonacci recursion. And their linear combination will also satisfy the recursive relation. Our objective is to find constant p and q such that f of n equals p times the first geometry sequence plus q times the second geometry sequence. We use the first two terms, n equals 1 and 2, to establish a system of equations for p and q. And we have a p equals 1 over square root of 5, and q is the negative 1 over square root of 5. And finally, we have the closed form formula for the Fibonacci sequence. That's all I have today. Thank you for watching.